The Third International Conference on Artificial Intelligence and Logistics Engineering, Mixed Parametric and Auto-Oscillations at Nonlinear Parametric Excitation. Mr. Alishir Alifov, Mechanical Engineering Research Institute of Russia, Academy of Sciences, Moscow, Russia. Equations. Nonlinear differential equations describing the system's motion have the form. We represent the nonlinear part of the elastic force in the form. In practice, the friction force is widely distributed in form, which was also observed under space conditions. Here are positive constants is the normal reaction force 4 and 4. Using the direct linearization method DLM, we replace this polynomial with a linear function, where are the linearization coefficients. We also use DLM for the friction force, part of which we represent in the form, where equations taking into account and take the form. Solving equations. To solve for, we use the method of replacing variables with averaging and the procedure for oscillatory systems with non-ideal energy sources described in and respectively. In this method, using the solution form. For the linearized equation, the standard forms of the equation are derived, which allow us to determine the non-stationary and stationary values of. And using 5, we obtain the equations of non-stationary motions, from which at equations follow for determining the stationary values of the amplitude and phase of the oscillations, where represents the load on the energy source, taking into account that in the expression in 3 instead of V, there will be. In the case of and small external forces, an approximate equality takes place for the magnitude of the stationary oscillation amplitude, and the load on its basis can be determined by the expression. The stationary values of the velocity are determined by the intersection points of the curves. Stability of stationary movements. Composing the equations in variations of the equations of unsteady motions and using the Rose-Hurwitz criteria, we have for speeds we have where represents the stiffness of the energy source characteristics. Calculations. The figure 1 shows the amplitude frequency curves for the velocity values. They completely coincide with the results of the well-known Bogolubov-Metropolsky averaging method. Solid line 1 corresponds to the linear parametric excitation. It's shown for comparison and denotes the self-oscillation amplitudes. The upper branch of curve 1, shown by the thick line, corresponds to stable oscillations, while the lower branch, thin line, corresponds to unstable ones. The dashed and dotted curves correspond to nonlinear parametric excitation. Figure 1 Amplitude Frequency Curves. Figure 1a takes place for a linear characteristic of elasticity. Figure 1b is soft and figure 1e is rigid. In the case of a nonlinear elastic force, there are no amplitude frequency curves at. There are no real solutions to equation 8. The horizontal line in figure 1b corresponds to, as can be seen from the graphs in the case of the nonlinear parametric excitation, reduces the amplitude at. It significantly narrows the frequency range and changes the shape of the amplitude curve. Within the shaded sector, for the steepness Q of the characteristics of the energy source, fluctuations with amplitude are stable. Sector with black color reflect rather weak stability. In this sector, the stability criterion 6 are met with values where. Thank you for your attention.